Okay, we're back. Um, so yeah, as I said, we did the Andrew Kelly things. I will link this video in the description. I heavily recommend going and watching this video in advance. So yeah, we talked about how what really plagues our programs today, such as I/O calls, like reading from files, reading from sockets, kernel context switches that are being made by I/O calls or other threading primitives that you might be using. The async state machine, the data that you are storing across await call sites, that is being stored in an async state machine. That thing is prone to optimization failures. So yeah, it's hard to optimize those kinds of code. Keep that in mind. And too many temporary heap allocations, as we said, within your code. If you have too many vectors that are being used to pass data around, you might find virtue in passing in pointers to existing allocations instead, or references. And the final point is thinking too verbally about code. So thinking too verbally about code leads to problems down the line in terms of your programming paradigm, how you think about your your data's representation, and the operations that you do on your objects or things, basically. So yeah, your programming paradigm affects these things. If you think too verbally about your code, that leads to optimization nightmares for the compiler. So I have listed a bunch of core mindsets for you to have in order to apply these optimization tricks, basically, and then we will jump right into applying these mindsets one by one on examples in Rust over here. That's why I opened this project. It's been open for 1 hour and we haven't really done anything on it yet. So yeah, core mindsets. The first mindset you should have is your hardware mindset and your program's executor. What do I mean by your hardware? In the first thing, we talked about how your CPU architectures and your extensions they exist. They are your target, and your program is a translation from source to machine code. This is where we apply that. So this doesn't only apply to Rust, but it also applies to all other programming contexts, such as JVM. For example, if you're writing Java code, your code is being compiled for JVM, which is interpreted by the CPU. It is not. It is also JIT compiled, if I remember right. There's like JIT compilation for the JVM, but if I remember right, it is mainly interpreted. There might be compilation going on behind the scenes, but as far as I know, it is a interpreted thing. So you need to be aware of that and consider the fact that native code might be faster than your code. If your program's executor in this case is CPU via machine code, as we talked about before, CPU can execute raw machine code in binary format. This is not machine code. We can see that these are string slices. They don't have machine code in this. If I scroll more up, yeah, I'm not seeing it. But yeah, CPU are an interpreter for the x86. Interpreting x86. Mainly being interpreted, but hot loops get compiled. Yeah, they get compiled into native code. That doesn't make it automatically the fastest in the quote-unquote native-like compilation target that is compiled to whatever the best native assembly is usually faster. Always the case, as I say again and again, perf your code, perf your things, benchmark your things. These things are for empiric results, not for theory. Runtime feature dispatch, NSWAR. We will talk about SIMD and SWAR later, but let's talk about runtime feature dispatch. So runtime feature dispatch is a thing where we discussed we have CPU extensions. CPU extensions you don't really know or assume when you're compiling your code for. Is x86 feature detected macro while you're writing Rust code. You somehow might have stumbled upon this thing. So this is a macro provided by the Rust standard library that lets you check for specific CPU features like AVX2 at runtime. So this is a macro that expands to false or std detect is feature detected AVX2. So this both depends on your target and the std detect runtime module. So this does runtime feature detection. If your target supports AVX2, you will be taking this branch at runtime. This branch will exist at runtime. What does that mean? So this else branch, if this feature is not detected, it still exists. Panic. Both of these branches still exist. If the feature that you're running on somebody else's CPU, let's say you're running this code on your friend's computer, and your friend's computer doesn't have AVX2, which is very, very rare, by the way, as we saw from the Steam hardware survey. But let's assume this branch failed. This is a runtime check. Your code is the same. Like, you compile this code once and you send your binary to both your friend and then you run the same binary on your computer. So both of these branches have to exist, and in this first branch you assume the CPU has AVX2 feature because you checked that before. And if on the else branch, which didn't match, you assume that the thing doesn't have AVX2, so you fall back to more general methods of using the x86 base architecture, what you have available at your hand. But we don't really do is x86 feature detected like this usually. Instead, we use crates like Rust runtime feature dispatch crate. If I remember right, there was like a crate that did that for you. Runtime micro architecture extension macro. Oh my god, I just forgot everything about this thing because the name is just so not rememberable. Please AI help me. What is the Rust crate for doing automatic runtime target feature dispatch? No, not that one. Multi-version, yes. Multi-version Rust. So yeah, we usually use this crate for doing specific CPU target dispatch. You just write one version of your function, and then the multi-version crate application of the target feature enable AVX for your function. AVX2 optimized. And then your function has like inputs, which is like a slice of things you can modify or analyze, whatever, basically. So that crate is being functions. It checks for the CPU capabilities once, and then sets the function pointer to that guy only uh, atomically, so the thing is optimized. So the function is being called optimize every single time you call it. It doesn't like do feature extraction every single time you want to call it. But yeah, basic usage is that you specify an x86-64 plus AVX plus AVX2. Your extensions go with separated by pluses over here. You can do things like SSE, or you can just read the documentation for this crate. I'm not gonna get too much into it, but yeah, you can do runtime feature dispatch like that. That helps users. Usually lower level libraries handle this for you, but in cases where they don't, or where you're rolling your own library implementations of physics, for example, or mathematics, you may want to do these, because you obviously don't want to have 15 different binaries your players can download and select from. Such an example can be found from Stockfish, basically. Stockfish chess engine. So Stockfish over on GitHub, in their releases page, they release multiple binaries. They release multiple binaries over here. Stockfish Android, Stockfish macOS, Stockfish Ubuntu, Stockfish Windows. That doesn't matter, that is OS. What matters is within Windows. Look at all these different things. So we have the ARM v8 target. This is a different CPU architecture. We will not get into that. This is like Windows on tablets or phones or something. We are concerned with x86-64, which is what most gamers use. So we have x86-64 base. This is just .zip. There's no extension over here. There's VNNI 512. We have seen this as the first entry in the Steam hardware survey. We saw that about like 28% of players have this. So 28% of players can go ahead and download this binary of your game. And then there's SSE41 POP-CNT, BMI2, AVX VNNI, AVX2. This is Stockfish doing manual compilations of their software for specific targets, and then basically publishing more than one executable. You don't really want to do this in your game, because in Steam people will just want to go ahead and download your game by pressing on an install button or download button and not go through figuring out what your extensions are. So what you really want to do is have just Stockfish Windows x86-64, and then when the player opens your game, you do your feature dispatch, which will let your gamers experience the speed of their CPU at runtime, and other gamers can also benefit from the same speed because their CPU supports newer features. And then they don't have to be basically they don't have to be constrained to just one CPU architecture with one set of features, because these features exist for a reason. They make code go fast. They're very cool. They're very nice. We should be using them. So SIMD and SWAR, the next topic in our list. As I said in Godbolt previously, the Godbolt website shows us the assembly of our program, which can contain these vector instructions that start with V's. These are also called SIMD instructions. If you don't know about SIMD, go ahead and read about it from AI or some other YouTube explainer. SIMD means single instruction multiple data. It operates on more than one data for doing a single operation repeated on multiple segments of data. This makes your code from 4 times to about 32 times faster. So this is a feature. This is usually some of these features are extensions, such as AVX2, SSE2. Makes your code go faster, but there's also a within a register. If I hello? Oh my god. Okay, my earphones were killing me, but yeah, we're back. SWAR means SIMD within a register, and what does that mean is that we don't really go ahead and reach for raw vector instructions over here. Instead, what we do is we operate on a machine word size. Type u size. Type word equals u size. This is usually your machine word size, the size of a pointer or the size of your register. So for example, for 64-bit architectures, this is racks, the size of racks, which is 64 bits, obviously. For 32-bit architectures, this is EAX, which is 32 bits, obviously. Why did I put IAX or EAX here? I have no idea, but yeah, when you talk about 64-bit or 32-bit architectures, 32-bit mostly doesn't exist nowadays. 64-bit usually assumed, but you are better off using U size, which is available within Rust, the target pointer sized thing. So yeah, you take the U size and interpret it as a list of U8s, 8 U8s. Basically, that is the idea. Or 4 U8s if you are 32 bits. So how you do that is up to many things. So you can go ahead and read the code on std_stir. Where was it? Let me find it. From UTF-8. There's all sorts of examples of this within both the std sort in Rust and both the stir validation checks. So yeah, we can see that it is obviously doing some usize bytes. It is doing some things with usize. It's checking for alignment, const things. If we can see here, yes, here is the thing. ASCII case, try to skip forward quickly. When the pointer is aligned, read 2 words of data per iteration until we find a word containing a non-ASCII byte. This checks for the alignment. Now we get a pointer and then we check for bounds. While we're out inside the bounds, we read, look, pointer, the add index, and then we cast it to a usize. The block is a pointer to usize. Then we read the first block and then we read the second block, and then we pass them on to contains non-ASCII. It's just a really simple bit check, right? There's a mask that is a repetition of this literal, which is basically just okay, right? So we have 80, right? If the U size is 64 bits, this thing is going to become this. If the U size is 32 bits, this thing is going to become this. So there's a bitwise AND check going on over here. So what this loop is doing is every byte is, as we know, 2 nibbles, right? 2 nibbles. These nibbles are 1 byte, and this checks the, I think, the topmost bit. Is it? Yeah. So in the binary representation of this is 1 0 0 0 0 0 0 0. This is 1 byte, 1 4 8 bytes. This is for the 64 bit, and this is for the 32-bit representation. So yeah, when you do an AND check with a string of, let's say, these bits, let's assume this is like, is this a string? It's not a valid string, for example. How did I know that? I did a mental AND on the first bits of these things, because an AND, how does that an AND work? It compares these, and if they're both 1, it's a 1. Otherwise, it's a 0. So in ASCII, the top bit is always 0. So this is the non-ASCII mask. So this checks for non-ASCII-ness. If it is not ASCII, we can check with using an AND, using the top bit basically. So for as you can see, we are man, English is so hard. I am so bad at typical English. we are processing 4 bytes or 8 bytes usually at once. This is the size of a U size, and with an AND operation we can produce. We can check for 4 bytes of text per how fast AND can run. So this is really fast. It makes your code go from byte for byte checking into a SWAR optimized SIMD within a register, because these don't really work on vector instructions. You won't really see V move-ups or instructions like that when this code is compiled. I mean, you might see it because your compiler might be very smart and see what you're doing here and compile the SWAR into a more optimized SIMD. That is out of the question right now. We will talk about that probably later, or maybe not. Well, yeah, SWAR lets you do SIMD even when you don't have access to the vector instructions or compiler intrinsics or really anything at hand. You can just pack bytes into an integer of bigger size and do your work on that using contains ASCII, which is like just a bit check. This is going to be really fast, and when this is fast, like this thing itself is really fast, and it also produces, like, it also processes about 4 to 8 bytes per iteration. You can assume how fast that is going to make things faster. What did I just say? I don't really know what I just said, but yeah. My throat is getting really hurt because I've been talking for so long. Yeah, that is the gist of it. And we saw software implementation of runtime feature dispatch, SIMD, and SWAR, and we can't really do these in software. But yeah, if we were to write JavaScript, and I could show you on Godbolt, we also have a JavaScript quote-unquote compiler here, V8. You can look at the optimized code over here within V8. You can also do that. That is very cool. As I said, make Godbolt your daily driver. We could see those. Do we have Java? Do we have Java? We do have Java. So you can look at the Java JVM outputs too. Let me take a bigger break, guys, because I will need some time to recover my throat because it's getting really harsh. Okay, I've been talking for a long time and I'm so bad at explaining things. I'm really sorry. I'll be back.